This is about where we ended.
Yep.
Alrighty. I remember towards the end I was rushing, and I think I left the impression that an antenna needs to be resonant in order to work well on HF bands or any bands. Is that correct? That I sort of leave you with that impression?
Yeah, that's the theoretical concept exactly.
Yes. So I'd like to backtrack a little bit, and then we'll get to part 2 and Smith charts and a little bit more under the hood. So when you feed an antenna with a feed line like Coax, and Coax, even the good stuff, has considerable loss when you get a high SWR, the question becomes, can I use a coax-fed antenna on more than one band? And the answer, of course, is yes, especially if you're clever and you come up with an off-center fed and a 4-to-1 or 6-to-1 balun and all sorts of other ideas. But here's another approach, and the NanoVNA convinced me of this. The antenna tuner, even if it's in your shack, at the end of a low loss feed line, like 600 ohm ladder line or window line, that will work well on all bands, even if it's not a resonant length up here. And a lot of hams, especially older hams, often do this because it's a simple way of having an antenna, one antenna up in the trees or whatever, work well on many different frequencies. So how does this work? It could be that the length of the antenna that you're asking to emit RF waves, when matched to something like a 600 ohm or 450 ohm feed line, this could result in fairly high SWR values right here. But because it's a low attenuation line, low loss line, we don't usually worry about that. As long as, what? As long as this device, the antenna tuning unit, whatever we call that, converts this weird impedance to something that the radio wants to see, 50 ohms, resistance, 0 reactance. Internally here, it's a little bit of magic. But what occurs is the radio just sees a 50 ohm load. It doesn't care what else is out there. It sees 50 ohms, so it sees essentially an SWR of 1-to-1 on this cable if this antenna tuner is doing its job. Has the SWR changed up here because you have a tuner? No. So at first it's like, well, wait a minute, why do I have the tuner? You have the tuner to make your radio happy. The tuner sees what it wants to see, 50 ohms. However, up here, you're not too worried about what the impedance is as long as the attenuation, the loss, is not significant. What do I mean by that? Oh, 1 dB, 2 dB, even 3 dB. I won't fret. 3 dB is half an S unit, but some people worry about that. So, no, the antenna doesn't have to be resonant to work well. The antenna system, the whole thing, needs to be resonant in order for the radio to be happy. So I hope I cleared that up. A lot of folks use a very simple wire that looks like this. 450 ohm window line is in fact less expensive than good quality coax, but over the HF frequencies has very low loss. So this type of line is easy to put up. Someone said, how long does it need to be? Any particular length? No, it just needs to go from the antenna to the tuner, no more, no less. So what you don't want to do is have extra ladder line and coil it up. You don't want to do that. So this is a standard all band 80 through 10 meter. If this wire up here is 100 feet, 200 feet, 300 feet. Now I wouldn't do this if the wire up here were 6 feet or 10 feet. That wouldn't work very well. But something that will work on the low bands, 100 feet, 200 feet, works really well. Here's the other way you can make a single antenna work well on all the HF bands. Just an odd length wire thrown into a tree. Now again, I mean, maybe 50 feet or longer. The length isn't critical. This is the critical part, this antenna tuner. What is it doing? It's converting whatever impedance you have here to 50 ohms. Little magic here. And it does that by working against what we call a counterpoise or ground. Now this isn't directly the NanoVNA, but I think I led to the conclusion that the NanoVNAs or VNAs let you find the resonant frequency of your antenna. That's true, but you don't necessarily have to operate only at the resonant frequency. So the SWR on the coax cable here, you want that to be low so your radio sees 50 ohms. What happens in the tuner is a little bit of the magic. So let me just stop and say that was the end of part 1, and I sort of rushed it the last time we met. Did you have any questions on what I said the last time or what I just mentioned here?
Yeah, I think we managed to close this part. I think we even
Okay.
introduced a bit of the you lift a bit of the or unveiled a bit of the Smith chart itself.
Okay.
But I think at least up to this point we were okay.
Okay.
Now
we're going to dig under the hood, right?
Exactly.
Okay. So Smith charts. I have to admit, 1 year ago, almost 1 year ago, I had never ever played with or used a Smith chart. Never. I'm not an RF engineer, and I was trained in sort of conventional ways, amateur radio. I passed all the tests, but I knew nothing. I just passed the test. So now we're going to see if we can look a little bit more at what's going on here and dig into this a little bit deeper about what the NanoVNA as an instrument can tell us if we can read a few graphs. Okay, so that's where we're heading today. So it's obviously a different looking graph. It's in what's referred to as polar form, polar coordinates. So we're going to look at what that means. So if I were to plot a graph here of x's and y's, often called an xy or rectilinear Cartesian graph, what if I plot reactance on the vertical, and here's 0, and resistance on the horizontal? Well, that would make sense. We plot a lot of graphs like that. But what if we take the reactance scale and bend it around, bend it around, bend it around? So now it looks like this. The resistance scale still is horizontal, but the reactance scale is still in ohms, 10 ohms, 20 ohms, 50 ohms, so forth. But we've curved these so that the higher reactants are over here, the lower reactants are here. So I'm going to look at this in a little more detail and then show you when we calibrate the VNA what that does. And it does quite a bit of magic. But we're usually not, or at least I'm not used to reading in amateur radio polar coordinates. So resistance is always plotted on what we call the horizontal axis, the x-axis. Now here's the catch. 0 is always plotted on the far left. Infinity, really large, is plotted on the far right. The center of the Smith chart, the bullseye, we can make that any value we want when we calibrate the instrument. What does that mean? We're going to go through that next. The other important thing to realize is the scale is not linear. It doesn't go 1, 2, 3, 4, 5. It goes 0, 50 in the middle. So 0, 10, 25, 50, 100, 200, 500. So it's a geometric scale. But the center, for most practical purposes, I'm going to force to be 50 ohm value. So resistance starts out here 0, and anything along this outer circle would have a resistance of 0 and then some reactance value. Anything along this circle would have a resistance of 5 and then some reactance. If I'm right here, the reactance is 0. So here's 0 ohms resistance, 0 ohms reactance. Not a very good antenna. Right in the center, we have 50 ohms resistance, 0 reactance. But if I move around here to where it says 1, and I'll show you an expanded view of this point right here would be still 50 ohms resistance, but 50 ohms reactance. That changes the impedance. If I come down in this direction, it's still 50 ohms resistance, but now 50 ohms of a negative reactance. That's what capacitors do. So the resistance curves all center around back over here, or their tangent over here. Reactance. So what is reactance anyway? I think of reactance as just a timing issue. And I'll show you what that means in terms of a very simple analogy of a kid and a grampy on a playground. Reactance means the voltage and the current are not in phase at the feed line antenna junction. That's all it really means. If it's a positive inductive reactance, we plot those clockwise, and 0 reactance, 10 ohms. Now this is still in ohms. 10 ohms, 25. We put a J in front of it to indicate it's the reactance component. 50 ohms. So you see, as I get more reactance, I'm bending around here. 100 ohms reactance would be a pretty significant value. 200 ohms reactance, and tighter here. This is also going negative 10, negative 25, negative 50. The negative means, again, it's capacitive reactance. The difference just being how capacitors behave in a circuit and how inductors behave in a circuit. And in one case, the voltage and the current are out of phase in one way, and in the other, the voltage and current are out of phase in a different way. But the voltage and current are not in phase at the same time, as long as there's any reactance. So, some values. Everything has an impedance of an R and an X. Now, the X might be 0, so we just indicate 0. So a resistance plots along this axis, horizontal, and a reactance, if it's positive, moves up, negative moves down. So where is 50 plus J0 located on the chart? Because that's a very important point. 50 is right here, dead center, and no reactance is, well, you don't move either way. So there's only one point on a Smith chart, one point, that has the unique value 50 plus J0, and I'm going to make that the bullseye. I'm going to make that the bullseye when I calibrate my VNA. Okay, so far?
Yep.
Okay. So, here's the clue. I want to be in the bullseye. Why? Well, because I'm making 50 ohms. When I calibrate the VNA, I'm making 50 ohms, the bullseye. I'll show you how I do that. My antenna, my coax, my radio, they all say they want to see 50 ohms. Now, I didn't make these things, and like what's magic about 50 ohms? It's just a number. But it's a number that's common for coax, and it's also a number pretty close to a free dipole in space, 50, 60, 70 ohms. So as hams working with coax, the impedance is pretty important. If I'm using coaxial cable that's 50 ohms, I want to make the system as efficient as possible. So we want to be in the bullseye because the bullseye represents 50 ohms, resistance, 0 reactance. That's where my coax wants to be. So let's jump back to what's the VNA actually measuring? Now, I wanted to skip this chart the first time around because it's starting to look a little intimidating. So the VNA is a clever enough gadget to measure what we call phase, timing. Unlike a crude SWR meter that says, oh, your SWR is 2, your SWR is 3. That's all it tells me, and it's not very significant information other than, it's not very good. So the NanoVNA measures what we refer to as a reflection coefficient. Sounds kind of official there. Reflection, well, something's coming back. Coefficient, well, it's just a fancy word for a number, right? So there's something that engineers call gamma, Greek letter gamma, and it's a ratio of the reflected voltage to the incident voltage. I can also describe that in terms of what's referred to as rho and an angle. These two are just two different ways of saying the same thing. And it's also, if you look at it in more depth, a ratio of the impedances. This gets into kind of complex math with lots of messy stuff that we don't want to deal with even in part 2. This is like part 6. But the reflection coefficient is a simple number when we look at its magnitude. Magnitude, fancy word for the value, the absolute value. So what if I have a reflection of 0? Well, then it's really easy. 0 over anything is 0. So my ideal antenna would accept all the energy on the feed line and radiate it all. It's not going to reflect anything back towards the transmitter. That's my ideal. If the reflected voltage is 0, the reflection coefficient is 0, because 0 over something is 0. That's easy. I want a reflection coefficient that's as close to 0 as possible, because that implies my antenna is radiating the energy, not shoving it back towards the transmitter. Now, engineers use something else, and I'm looking, I don't know who of you might be an engineer, but engineers use a term referred to as return loss. As a ham of 60 years, I had never heard that expression, and I had to think, what is this? Return loss. Well, return, something's coming back. Loss. Well, I understand what the words mean. So its value is negative 20 times the log of rho. No, I'm okay with math. The log of rho. All right. Rho is 0 to 1. So I know the log of rho is going to be what? A negative number. A negative number times a negative 20, that's a positive number. So return loss comes out to be a positive value. Rho is the absolute value of gamma, okay. And return loss is just a number in decibels, in dB, because it's a ratio. 20 times the log of rho. Okay, I think I get what that is, although I've never used it before. So when we look at the voltages on a feed line, this is what I was taught, and I kind of memorized this to pass the test and get my license, that if you have a feed line that has a SWR other than 1, you've got a return signal, and that return signal mixes with the signal going out. You get a standing wave. Well, I knew what that was because you can show that with just a rope in a tree. So the ratio of the maximum voltage to the minimum voltage is some number. Okay. Max to minimum, we can call that an SWR value. Okay, so I get what SWR is in terms of looking at the voltages on a feed line. It's also equivalent to 1 plus rho over 1 minus rho. Ah, I thought, I've never seen that before. Let's check this out. So if I want a perfect antenna, rho is going to be down here. The return loss is going to be infinite? What? Let's check that out. I want a big return loss. See, that doesn't sit well with a lot of folks. Big return loss. The SWR 1. Well, I remember that. I want a low SWR. Well, I can't get any lower than 1, right? All right, so reflection coefficient, or rho. Let's start with the basic one. It's just a number, and it's just a simple ratio, because I'm not going to worry about the complex impedances here. It's somewhere between 0 and 1. Or I should say equal to, actually, here. 0, less than or equal to rho, less than or equal to 1. Okay, so if it's 0, I'm really, really happy. That means there's nothing reflected. That means I assume the antenna is perfect. It's radiating it all. If it's 1, that means it's absolutely the worst antenna possible. All the energy is coming back. It's not radiating anything. I don't like that. So I think I get in my mind what rho is. Rho is just perfect to imperfect. Return loss, let's take a look at this now. Negative 20 times the log of rho. The log of rho, okay. I know it's got to be a positive number because the log of rho has got to be a negative number. So let's check this out. When rho is 0, I'm happy. So the SWR is 1 plus 0, that's 1, over 1 minus 0. Well, that's 1. Well, 1 over 1 is 1. Oh, I like that. The SWR is 1, or Americans say 1 to 1, but it's just a ratio. It's 1. When rho is 0. So if my SWR is 1, I'm really, really happy. So here's just a quick table I threw together to sort of give me a ballpark feeling. So if my SWR is 1, my antenna is perfect. The reflection coefficient is 0. Nothing's coming back. That means what's coming back? Nothing. I've lost all of it. Oh, now I get it. So the return loss, I want to be all of it. Big number. Infinite. So now I get it. I don't want anything coming back. So if my antenna is radiating everything, it's lost everything on the way back. That's sort of a backwards way of thinking, but it works. Well, often my antennas have an SWR of 2. And I don't get upset. 2 isn't so bad. 2 means the reflection coefficient is 0.3. I'm thinking, whoa, 0.3? That's 30% of the voltage is coming back, 0.3. I don't like that, but my radio's happy. I work contacts all over the world, so that must not be very bad. Okay, when my SWR gets to 3, sometimes my radio doesn't like it. It starts going beep, 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 beep. Fix it, fix it, fix it. So an SWR of 3, now I'm saying measured in my shack on my feed line. An SWR of 3 is a reflection coefficient of 0.5. That sounds way, way too high. I'm getting half the voltage back coming from the antenna back to the radio. Now, I'm not worried right now what happens to that, but it's on the way back. It's in the wrong direction. What can I do? Well, 0.5 voltage, I know power is V squared over R, so if it's 0.5 a voltage, it's 0.5 squared, 0.25. Oh, 25% of the power is coming back. So, all right, now I get it. If I'm sending out 100 watts and 25 watts is coming back from the antenna towards the transmitter, my SWR is by definition 3 to 1. Oh, I don't like that. But, I know if I lose a little bit of energy, the guy at the other end is not going to worry about it. So if my SWR is 3 and I've lost a quarter of the power, the other guy might say, oh, I think maybe you're a little fainter. It's not going to make a difference. When does it make a difference? When do I really worry? Well, maybe when the S meter on the other guy's radio drops by 1. S8 to S7. So I've lost a little bit there. That's 6 dB. So if I lose less than 6 dB and I'm still talking to somebody, I'm not going to worry. So I'm not going to fret trying to make the SWR perfect on my antenna system. That's a waste of my time. That's what I wanted to show here. But what happens when you get higher SWR values like 9 to 1? Oh, yikes. Now I've got 0.8 reflection. 80% of the voltage is coming back. 0.8 squared, 64. So about 2/3 of my power is coming back. Oh, I don't like that. What am I doing here? I'm just heating up my coax. That's silly. I got to fix the system. So let's come back to the NanoVNA, because that's a cool tool. The NanoVNA, in a way, is out of the box dumb. It's not quite dumb, but it's pretty dumb. I have to teach it because of the internal circuitry. I have to teach it what's a 0 ohm load, an infinite, really, really high ohm load, and mostly what's a 50 ohm load. So they come with these standards, and they just screw on the end of the NanoVNA on the SMA connectors. Now, usually the open and the short, well, they're easy to build. Open is nothing's there. A short, just put a wire and short the pin. But the L is the key. The L needs to be a fairly good high precision 50 ohm non-inductive resistor. So there's the expensive part. If I take the L and open it up, pliers, hammer, or something, I should find a little 50 ohm resistor in there. Now, I always wanted to just take the hammer and open it up and look, but then I'd ruin it, so I don't want to do that. But I'm sure what's in there is a pretty good 50 ohm resistor. Okay. You can put those standards on the end here. Where's my cursor? You can screw them on there, and if you type the right buttons here, you can calibrate your device over some frequency range using the S, the L, and the O. I did not do that here. Why not? Because I hated reading this little tiny screen. And I hated finding my way through all these menus. It's kind of a mess. So I did all this on VNA Saver software, which on Windows 10 worked well, and it was free. So I started to think, well, I'm doing the calibration right here, right? So this device sees this as my calibration plane, the location. So when I put on the 0 and say, all right, plot a Smith chart while I'm doing this. So I say, okay, here's 0 ohms. It's a short circuit. And I say, all right, show me the Smith chart now. And I say calibrate. It plots it right here. So 0 ohms during the calibration process plots here on my Smith chart. Now, I'm looking at this on the VNA Saver software, but you can do it on the little screen on the device itself. It just won't look so big and pretty. All right, then I say, okay, I'm going to put on the O standard, the open. The open means there's nothing connected. That plots over here. Now I'm on the resistance axis, remember? 0, infinity, or, 100,000 ohms or something. Now the key. I screw in the 50 ohm load and it plots right there. It better plot there or I'm in big trouble. So I'm forcing during the calibration process at some frequency to tell my little NanoVNA 50 ohms, the bullseye, that's where I want it to be. And it remembers that if I save that calibration file. Now, I have to do that over some frequency range. So what I traditionally do is say, all right, VNA, I'm going to calibrate you over 80 meters. So I sweep from, let's say, 3 to 5 megahertz. And I do this. The S, the L, the O. Then I say, okay, let's save it. So I save it and I say, calibration, 80 meters, ADM. Say, all right, now I want to do it over 40 meters. So I do the same thing from 7.0 to maybe 8 megahertz. And again, 20 meters, 14 to 15 meg. So I make like 8 different calibration files, each for one particular band. Now, why didn't I just say, well, calibrate 1 to 100 megahertz? I could do that, but I don't, that doesn't feel right. I want to get as good a calibration I can over a small frequency range. Because after all, my computer can store all these files and I don't care. Now, if you're on the little NanoVNA, I think it only allows the one I have 5 calibration files. So then I'd have to rethink, well, what I want to do, 80, 40, 1 to 10 megahertz, 10 to 100, you know, that's a different story. So I've now calibrated my VNA over 80 meters, 40, 20, 10, 6, 2 meters, 440. I don't go up to the gigahertz. So if I had calibrated it right here, I only have, I think, on mine 5 files that I can save. When you first turn this on from scratch, I think it automatically loads calibration file 0. Only an engineer starts with 0, right? 0. But then on here, I can go click, 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 and pick any calibration I want. I do not, this was the question last time, I don't have to calibrate this every time I use it. No, that would make it awful. I'd waste time. But I do have to calibrate it and save the file either on the device or in my case on the computer. So any questions up to that point? The calibration process is critical.
Only one question. I'm
Yes.
sorry.
Yeah, no.
Why the open circuit? Why we have to put the connector there? If
I tried it with not doing that, and I got the identical result. But I think here's the catch. If you calibrate up to 1 and 2 and 3 gigahertz, then even little connectors make a difference. But 80 and 40 meters, no, it didn't make any difference. So I tried that. I didn't want to mention it because waste time. But I thought, why do I need an open connection and an actual connector on there? Well, you do because at 1 or 2 or 3 gigahertz, that little extra connector is important. That's a good question. I should have mentioned it anyway. So at 80 meters, I don't care about 1 or 2 or 3 inches. Now, here's the thing that I learned well into my career as a NanoVNA instructor. Hey, why did I do this? Let's say I have 100 feet of coax to my antenna. Well, why don't I calibrate my VNA at the end of my coax? Now, I'm not going to go out and climb a tree or a tower and do all this calibration up in the air. But hey, I've got another 100 feet of coax behind me here. So how about if I take my 100 feet or 100 feet of RG213? Why 100 feet? No special reason except you buy it in 100-foot lengths. Oh, and there's another good reason. 100 feet's about a half wavelength on 80 meters with a velocity factor of 0.7 or so. So, yeah, 100 feet is about, give or take, it's a half a wavelength worth of coax on 80 meters. All right, good. So now I take my little NanoVNA, put on a little adapter to go to the PL259, put on 100 feet of coax, then I go back to an SMA connector, and I say, all right, now I'm going to recalibrate my instrument, but at the far end of 100 feet of coax, which is just, behind me here. I do all of that. Now I save this, and I save it as, what do I call it? End of 100 feet of coax, something, I can name it anything I want. And I save that. Why would I want to do that? Oh, so now if I connect my VNA to my real coax, and it's 100 feet, and at the end is the dipole, then whatever the impedance I measure, I got to be careful because I have this all connected, to the Here, see what I've been doing here? I built my own circuit board here. So it all fell apart, but I knew it was going to do that. I'm going to unconnect a connector for a moment here.
Take your time.
See, that's what I'm afraid of. That falls on the floor and I break it. So let me just take the coax part out here.
That's a nice breadboard over there.
Here, I can connect it here. All right, done. Now I know I'm not going to drop this. So now what I've done is I've calibrated this at the end of 100 feet here. I could also take the end and connect it to here and get the through measurement. So that's not needed for antennas, but it's needed for filters and things. So my through measurement is through 100 feet of RG213. So you might think, oh, that's kind of wasted time. There must be better ways of doing that. And yes, there are. But I tried this to see if it works, and it worked beautifully. So I thought, oh, that's cool. Can I do that with my MFJ and Rig Expert antenna analyzer? No. So someone said, well, why do I need one of these? I have an MFJ antenna analyzer. Why do I need a NanoVNA? And I said, I don't know. I've got two MFJs next to me. I still like to use this NanoVNA much more. Sort of like the difference driving a stick shift and an automatic. I don't know. But this was cool. It worked. So what do I really want to know? Do I want to know the impedance up at the antenna? Maybe. Or do I want to know what's the impedance of my feed line in my shack? Because I want to know, can it mate with my radio? And if it doesn't, then I need an antenna tuner to do the matching. Oh, does that make sense? That I can calibrate this at the far end of my feed line. What if I had 200 feet of feed line? Okay, so I calibrate this at the end of 200 feet. You see that you can't do that with a Rig Expert? Okay. I don't hear anyone shouting, wait. So,
yeah, I'm just thinking out loud.
yeah. So, in other words, I've moved the calibration plane at the far end of 100 feet of RG, good quality, 50 ohm coax. So I don't have to do that, but I like that I can do that.
Yeah.
It's like my car has 6 gears. Even if I never drive it in 6th gear, I like having that 6th gear. So, if we're clever enough, we can move the plane from the shack right out to the antenna. And it doesn't involve any of this math. Okay, so I want to prove that to you now. Ready? Prove it to you. So I just have my NanoVNA in my shack, and I connected to 100 feet of good quality RG213, and I connected to a 10-meter vertical antenna, one that I bought, didn't build, but I could have built it. So I take a look at it, and the SWR from, this is SWR from 28.0 megahertz to 29 is 1.5 to 1, drops to 1.0 something, perfect, and back up here, and even back up here it's less than 2 to 1. So in other words, this antenna will work over the whole 10-meter band for me. I'm quite happy with it. And it's tuned to the low end of the phone band, which is where I like to operate, or even down here in the CW part. So this is a perfect antenna for me on 10 meters. 100 feet of good quality coax. I don't have much attenuation. Don't worry about it. Here's the Smith chart. Oh, we're going to get back to Smith chart, are we? Okay, so look at this Smith chart. Little curlicue figure 6. Where do I want to be? The bullseye. Why? Oh, because that's 50 ohms. The SWR is probably going to be lowest at the bullseye, is it? Well, let's see. The SWR is lowest right here, pretty close to marker 3. Marker 3 is 28.4. Oh, I like that frequency. It's right in the middle of the low part of the phone band. So here, I hope you can see this number. Here's marker 1, 2, 3. Here's 50 ohms, bullseye. 4, 5, 6. So even out here, way out here, far from the bullseye, the SWR is still 2 to 1, or a little less than 2 to 1. I'm very happy. The antenna works great. Now I'm thinking, okay. What if I add some feed line? How much? Well, let me think. I remember on 10 meters, a quarter wave from Mobile was about 8 feet. 8 feet, quarter wave. But I'm in Coax. Coax has a velocity factor of about 0.7. So how about an 8.5 foot antenna times 0.7? So about 6 feet. I'm just ballparking a figure, 6 feet. So in other words, 6 feet of coax, RG213, 6 feet, that's about a quarter wavelength of coax. I'm going to add a quarter wavelength of coax and see what happens. How do I add it? Well, I put on a little barrel connector, another 6 feet, and then back to my NanoVNA. I didn't cut off 6 feet from my coax. I could have, but then I couldn't splice it back in, so I didn't want to do that. So if I add 6 feet, I want to stop and ask you guys, what's going to change here? Will the Smith chart change? Yes or no? Will the SWR graph change? Yes or no? I'm going to stop talking, and I want you guys to unmute and call out an answer. I'm adding 6 feet and not changing anything else. I'm certainly not changing anything at the antenna. I'm just adding 6 more feet of good quality coax. Will either of these graphs change? I'm going to stop. You guys talk for a moment.
Probably not.
And you can talk in Portuguese. I'm not going to force you to talk in English.
A quantidade coaxial que lá chega deve ser irrelevante. Desde que, bom, se tiver lá balão, tanto melhor, mas em princípio não altera nada, não é?
Recording has stopped.
I would say
you don't want to record your responses, I can tell.
You don't want it to look dumb in YouTube.
Yeah, but hey, look, we're among friends now. So,
yeah,
will the Smith chart change?
That,
yes or no? Will the Smith chart change?
Yes. I would say yes.
Yes. Will the SWR graph change?
No.
How about that? All right. So we have one volunteer. Do we have anyone else that wants to try a different view? Silence.
For me, no change.
No change. All right. I recognize that voice now. That's Ricardo?
Yeah.
Yeah, see, I know you guys now.
Yeah.
Okay. So we're going to add 6 feet of coax. Will the impedance change? Yes. Why? Oh, we better figure that out. Will the SWR change? No. Why not? Let's take a look at this. Here it is. Oh, wait a minute. This was a figure 6. Now it's like a figure 9. The Smith chart has moved, what? About 180 degrees. Oh. But what's the closest point to the bullseye? Still pretty close to marker 3 or so. Maybe 4. Somewhere in here. So what has the Smith chart values done? They've rotated around the Smith chart. Isn't that cool? Why do they do that? Ah, so that's that's under the hood, right? Why do they do that? But wait a minute, look at the SWR. Let me go back to, see the SWR graph? No change. Well, maybe a teeny. I mean, 6 feet's a little more attenuation. Not enough to measure here. Now, if I added 600 feet, yeah, that would change it. So, Ricardo, why did the Smith chart rotate?
Because it's malfunction. Sorry, but perhaps with a balloon. With a balloon,
a balloon.
The coax.
Oh. No, that's a great question. No, it would make no difference.
Oh my.
No, nothing to do with the balloon.
I give up.
Yeah. And if you would ask me to explain it, for me in English, a year ago, I'd be lost. Now, I knew the SWR, once you measure it in a cable, doesn't matter where you measure it. I kind of remembered that when I was a kid, at least on 80 meters. But why does the impedance change? Oh, the NanoVNA can show me, because what are we looking at? A ratio of voltages, but the voltages are different at different points on the line. So you have the voltages going this way and this way, creating a standing wave, right? I can visualize the standing wave. So if the voltages are different, the currents are different, the impedances are different, the phase is different, and watch out, the resonant frequency is also different. What? Now, I'm not saying the resonant frequency up at the antenna changes. I'm saying the resonant frequency, what do I mean by that? I mean where the reactance is 0. That will change if I add or subtract coax. Because the coax isn't neutral, it's acting like a transformer. In fact, it is a transformer. Wait a minute. Now do you see it? So the coax has inductance and capacitance. It has a characteristic impedance. We say it's 50 ohms. So that means think of the coax as little inductors and capacitors. So as I add more and more feet of inductors and capacitors, I'm going to change something about the resonance of the circuit, the whole thing. Now do you see it? Am I giving it away? The coax
Okay.
is part of the antenna. Oh, we say, no, it's the feed line. No, it's part of the antenna. So here's a way you can look at it. Let's say I have some feed line. Now, it could be coax, anything, but this is just drawn as, parallel lines here. I have some load. That's my antenna. Some Z's are a source. So here's a feed line feeding an antenna. And let's say at some frequency, this lands on the Smith chart right here. So my antenna is right here. Not at the bullseye. That's important. Not at the bullseye. So if I move towards the transmitter, I'm going to move this impedance around this far if I have 1/8 of a wavelength of feed line. I'm going to move around halfway here, 180 degrees, if I have 1/4 of a wavelength. Quarter, that's an interesting number. So a 1/4 wavelength moves me halfway around the Smith chart. It's like, whoa, that's kind of interesting. 3/8 of a wavelength moves me here. And if I had made this slide, I would have said, what if I have a half a wavelength? It gets me right back where I started. So in other words, this is kind of interesting. And I had to really stop and think about this. And I was puzzled for why. Why does a half a wavelength of coax at some frequency repeat the impedance? Can anyone explain that? In Portuguese or in English? That's a tough question. Even for an engineer, that's a tough question. Why? What's magic about a half a wavelength of feed line at some velocity factor and at some frequency?
The phase
What about the phase?
turned to be equal again.
Okay, yes. Why? It's sort of like saying a circle's a circle because it's circle shape. So I don't quite understand why. But that's a pretty good answer. That's a pretty good answer. So this is what happens on a feed line when the SWR is not 1-to-1. Now what if I have a feed line, some antenna, and it's 1-to-1 SWR? Then if I add or subtract coax, doesn't make any difference. It's already perfect. I had to stop and think about that. The impedance moves around. So what's it doing? It's moving around, but watch. It's moving around, but never getting closer to the bullseye. Why? Because the SWR is not getting any better. The impedance is a different number, although the SWR is not. It's like, how can that happen? Oh, see? What is SWR? SWR is a scalar quantity. It's just telling you what's coming back, but not the phase, not the timing. So a lot of simple, cheap SWR meters, they just measure power this way, power this way. They make a little meter with a, So if I know on my SWR meter, the SWR is 3-to-1, I don't know what to do about it to make it any better. But on my NanoVNA, if I plot it on a Smith chart, I could look at it and say, oh, my SWR is 3-to-1, but in my shack it's inductive. I need to cancel that inductive reactance in my shack because I'm not going to go climb to the top of the antenna. How do I do that? Well, little coils and capacitors. That's what I was playing with over here. So I better keep going or we could spend a lot of time right here. This is the key to why the NanoVNA is worth $50. It tells you the phase, the timing. Really, really important. So I made it red. Really important. So whatever happens out at the antenna, I can measure that in my shack and calculate what's going on at the antenna. So here's the thing. If you change the length of the feed line, the magnitude, that's just fancy word for the number, the size of the voltage and the current, they're changing along the line. If the SWR is not 1-to-1. The impedance is changing. What does that mean? The resistance and reactance values are changing. The phase is changing. Well, that's changing because the voltage is changing. And watch out. The resonant frequency is changing. And I had a ham say, come on, Barry, you're wrong. Once I build the antenna, the resonant frequency of the antenna is fixed. I said, well, sort of. You're measuring it, though, in your shack. Now, because your coax, remember, your coax is a series inductors and parallel capacitors. You've messed with a little bit of feed line that's moving that resonant frequency around. What does resonant mean? It just means no reactance. So I can change the reactance by changing the length of the feed line. I can't make the SWR any better. To do that, I have to go up and chop off 10 feet of the antenna. So the SWR does not change other than a little bit with, a little attenuation. Now, what if I added 1,000 feet of coax? Yeah. Well, because there's so much attenuation in coax, my SWR looks like it's 1-to-1. So let me stop and say, that's really important. I had to read this and think this through until I said, oh, I get it. The NanoVNA is telling me why my SWR is 3-to-1, not just the fact that it is. Let me stop. Does that make sense, sort of? I mean, you're hearing it in English, so you've got to do some translation here.
No, it's not the translation. It's really the affecting the resonant frequency. It's kind of
so here's the key: the
it's
resistance.
Kind of weird statement, right?
Yes, yeah. So the resistance, the reactance, the impedance, the resonant frequency, all of those will not be the same at the antenna and in my shack where I'm measuring it comfortably, will not be the same unless my feed line is an exact half a wavelength at that particular frequency, or 1 wavelength, or 1.5 wavelength. It's got to be an integer multiple of half a wavelength. That is super, super important. Good physics there. Okay? So right away I've thought, oh man, the NanoVNA is worth $50 or $100 or maybe even more. So the reflection coefficient does not change with length. The return loss does not change with length of feed line. The SWR doesn't much change with feed line. So these things are what an engineer or a physicist might call, these are scalar quantities. There's no timing involved. The phase doesn't matter here. These things are determined by what? What happens when the feed line hits the antenna? That's where the SWR is determined by, right there. If there's a mismatch there, it's a mismatch all the way down the coax. So the SWR, I could measure it at my antenna or measure it in my shack. I'd rather measure it in my shack because it's more convenient. Okay? Now, let's get back to why I started this. Resonance. What does the word mean? We use it all the time as hams. And most hams, when I tell them, all right, we use this word all the time. Tell me what it means. Silence. Come on, you use this word all the time. Resonance. What does it mean? Silence. And then someone will say, it's where my SWR is lowest. And that's the absolute worst answer. It's not. The resonance is just simply where there's no reactance in the system. No reactance. Means you're back in phase. But it's not the lowest SWR. So let's take a look at that. I'm going to do something that I was told, you're behaving like a third grader. And I said, good. Third graders might understand this, whereas adults are trying to figure it out in fancy words. So I had a grandchild, and she was very young. Now she's 8, so she's getting older. So what do we do when we go to the playground? She jumps on the swing right away. What's my job? Well, everybody knows my job. I've got to push her, right? So how does Grampy know when to push? I'm going to stop. Look at this picture. Every Grampy knows when to push. When should Grampy push? Well, you push so the kid swings higher, right? But when? When does Grampy push? Now, if you look at this, you see Grampy and grandchild. I look at this, what do I see? I see an end-fed dipole. What's Grampy? The feed line. What's the grandkid? The current on my antenna going back and forth. Oh, you see why I like this? So what does my grandchild tell me? She says, Grampy, push in phase with my natural period of swing to increase my amplitude. She doesn't use those words. I wouldn't expect her to. But she knows, intrinsically, she knows when I should push. I should push when what? Her swinging comes right back to the end, and for a moment she stops. That's when she's ready to go forward again, and that's when I should push. She knows that. Come on, Grampy, get with it. So what does this mean in terms of antennas? The push, the feed line, is matching the natural vibration of the kid on the swing, the current. That is resonance. And if I explain it this way, I've had some hams say, oh, come on. I said, look, this is a good analogy. We all know what it means to go to the park and push your grandkid on the swing. So, resonance. The input push from the feed line, that's Grampy, needs to consider at least the kid on the swing, needs to be in phase with the natural vibrations of the grandkid, the current in the antenna conductors. We call this situation, this phenomena, resonance. Let me stop. Do you like my analogy?
Yes, very good.
Okay. Haven't said resonance is lowest SWR. It may be, but it doesn't have to be. Okay, so that's resonance. So, what happens if Grampy pushes too soon? Well, I know, because sometimes that happens. She's still swinging back, and I start to push, and we crash. Grampy, come on, wake up, Grampy. So, what if I push too late? Well, that's worse, because she's starting to swing down, and I'm running after her. So, in either case, she's not going to add the amplitude, right? In either case, we have a phase error. Do you see where I'm going? A phase error is a timing error. It doesn't mean I'm pushing harder or not so hard. It means I'm pushing at the wrong time. Now, again, think of this as an end-fed dipole. At some frequency on my radio, the antenna current, is going to go back and forth, right? The frequency is determined by my radio. Grampy is just, getting instructions from my radio when to push, right? Grampy's the feed line. So, what are we going to do here to make this better? If the feed line and the current on the antenna are in phase, we have a situation referred to as resonance, the maximum current, the kid swinging higher. Well, why is that good? Well, first, the grandkid's happy. She wants to swing higher. And what's the other reason? Well, more current on the antenna means more EM wave generated. The electromagnetic wave is proportional to the size of the current. So where is this current? Well, even though I may feed it at the end, the current is always maximum at the center of a half-wave dipole. So what part of the dipole is doing most of the radiating of the EM wave? Not the end. I'm just feeding it at the end because it's convenient. The center of the dipole. Now, most of our dipoles are probably center-fed, but the Grampy example is end-fed. But I think you can see it's okay. So the radiation is maximum, the EM wave generated is maximum, if we can get in phase happening right here. Now, when I show the voltage here, that's not the voltage I'm talking about. I'm talking the voltage on the feed line pushing the electrons back and forth. Now, I asked a question because someone asked me a question, and I thought, no, I'm missing something. Here's the question. You have to stop and think about this. So on the antenna, we've got, let's say, electrons moving, right? Accelerating electrons. Okay. Where do those electrons come from? So my question is this. Do the electrons that are accelerated on the antenna, do they come from your transmitter? Yes, no. You call it out. Unmute. Do the electrons that are vibrating on my antenna, do those electrons come from my transmitter? Yes or no? Or silence?
Yes.
I heard yes.
I don't
know how many here, but not everyone's volunteering here.
I look at this as a wave, and I think the transmitter give a push, but the oscillation of the electron to forward and back is local, more localized in the antenna, perhaps. I don't know.
Good answer. Okay. And I think if you had said it in Portuguese, I'd probably understand it because I can see the vibrations there. The electrons were already in the antenna. They didn't come from the transmitter. The instructions came from the transmitter. Now, an engineer might say, well, the electric field gave the instructions. So, no, the electrons don't start out on the radio and go up the feed line into the antenna and then all the way back to the radio. The electrons hardly move at all. So the electrons that generate the electromagnetic wave in your antenna, they were already in the antenna because the antenna is probably made of copper, aluminum, something that's a conductor. Now, if I make an antenna out of plastic, it's not going to work very well because there's no charge that can move in that. So that was sort of a loaded question. So the electrons were already in the antenna. What did the feed line do? The feed line just told the electrons how to move. So Ricardo's answer was right on there. All right, so what happens if I'm off the resonant frequency? I know I can still, use my radio. I get contacts all over the world. So what happens? If I'm operating below the resonant frequency, we say, okay, the dipole's too short. I need to make the dipole longer. Well, I'm not going to climb up and add 10 feet. It means the current leads the voltage. What does that mean? It means the kid is swinging back and forth faster than Grampy's pushing. You see it? So that's a bad phase error. We just call it capacitive reactance. Now, calling it something doesn't mean we understand it. That's a common misconception, I think. Giving a phenomena a word doesn't mean we understand it. We just give it a word. So the timing is wrong. Grampy's not pushing at the right time. So what if I operate above the resonance at a higher frequency? So here's a dipole cut for 3.8 megahertz, and I want to operate at 3.95. That doesn't work. I got a high SWR. Why? Oh, now the dipole's too long. To operate at a higher frequency, right? That's a shorter wave. I need to cut the antenna back 10 feet. Well, I'm not going to do that. So I've got a timing problem, a phase problem. Grampy's not pushing at the right time. Now, in English, we have this phrase, Eli the Iceman. I don't know if there's an equivalent in Portuguese. ELI. L is an inductor. E is electromotive force. Fancy word for voltage. I is current. Why is I current? I is current because the man named Ampere thought of current as the intensity of the charge. Intensité in French, intensity in English, it's still a letter I. So Ampere started to call current I, and we just stuck with it. So Eli means for an inductor, the voltage, E leads the current. Okay. Iceman, ice. The C is a capacitor. Here the current leads the voltage. So this is kind of a little mnemonic to remember which way it goes, but that's not important for us. What's important is I want my antenna to work well. And if I'm operating off the resonant frequency, especially on 80 meters, I get a high SWR and my radio complains and I can't do it. It won't work well. What do I do? Well, what do I do? Every ham knows what to do. I'm not going to climb the tree and add 10 feet of wire. I want to fix my problem. It's like, Grampy, push at the right time. Grampy's not paying attention. Because how does Grampy push? Grampy pushes based on what the radio frequency dial is. So what do I have to do? I have to cancel the reactance that's happening at the antenna. How do I cancel reactance? Well, that's a good question. So now we have to look at an antenna like a half-wave dipole, like this circuit. It has some resistance. Yeah, dipoles are like 50 ohms, 70 ohms. It has some inductance and capacitance. I don't see those. Well, wires have inductance. And by the time the charge gets to the end of the antenna where the insulators are, that's a pretty high capacitor. So, yeah, antennas also behave like inductors and capacitors. So what happens if the L and the C cancel each other? Oh, that's the resonant frequency. That's when Grampy's pushing at the right time. But what if I have too much L in my circuit? Then I need to cancel the L with C because C and L, they push at the opposite time. So the reactances are in ohms, but they work in two different ways. It's like Grampy pushing too soon or too late. So this is the key. Can I cancel the reactance that appears on the antenna? Can I cancel that in my shack? Yes, mostly. So let's take a look at how that would work. So we're coming back to Smith charts, and I'm looking. It's already 5 o'clock, so I could go for another 3 hours, but I got to speed this up a little. So what if I have a perfect antenna? The rho is 0, no reflection. It plots right in the center. I made these arrows right in the center. There's only one spot where rho is 0, and only one spot where the SWR is 1:1. Or I had another ham say, why do you say 1:1? Why don't you just say the SWR is 1? It's a number. You don't have to say 1:1. He's right. 50 ohms. So that's perfect. My antenna does this. I'm good. But what if I get a little bit of reflection, like maybe 20%, 0.2? Then the SWR plots anywhere along the rim of the circle. Wait a minute. What do you mean anywhere? Well, the impedance is changing as I go around. Here and here, it's a pure resistance. Up here, it's a resistance and a reactance. Down here, it's a resistance and a reactance. But any combination here results in the same identical SWR of 1.5 to 1, and I'm fine with that. My radio's happy. So if I know the SWR, do I know the impedance? Yes or no? Silence. If I know the SWR is 1.5 to 1, do I know the value of the impedance? Yes or no? Silence.
We know the reactants.
All I know is I'm somewhere on this circle. Let me come back. I lose my mouse. If my SWR is 1.5 to 1, the reflection coefficient is 0.2. That means I'm really from the bullseye 2/10 of the way, 20% of the way to the rim, because I'm getting this. The rim is the worst. So all I know, if the SWR is 1.5 to 1, my impedance is somewhere on this circle. I don't know the resistance, and I don't know the reactance. I just know I'm somewhere on this circle. So there are a lot of values of impedance that result in the same identical SWR 1.5 to 1. I didn't realize that. I thought, oh, the Smith chart is telling me that. But I didn't realize it. I mean, if I go back 10, 20, 60 years. How about if my SWR is 2 to 1? Often my antennas say 2 to 1. The reflection is 0.3. What does that mean? From the bullseye, let me get back. From the bullseye here, I'm 30% of the way to the rim, 0.3. SWR 2 to 1. That means my impedance is somewhere on the rim of this circle. Somewhere. I don't know where. In fact, if I add or subtract coax, my impedance is going to move. But will my SWR move? No. Do you get it now? So the Smith chart is telling you much more information than just the measly SWR. I can get any cheap meter can tell me the SWR. Actually, the NanoVNAs, they're as cheap as my old meters. So this is really interesting. I don't know the impedance. I don't know it. Except whatever it is, it's somewhere on the rim of this chart. So now my SWR is 3 to 1. My radio's not so happy. In fact, some radios start to fold back on power. The reflection coefficient is 0.5. What does that mean on the graph? I'm halfway to the rim. The center reflection is 0. So here, 0.5, 50%, I'm halfway to the rim. What's the rim? Well, as you see, the rim's going to be reflection, everything, 1. So if my SWR is 3 to 1, my impedance is somewhere. Now, if the impedance is here, I can figure it out, because it's 1/3 of 50, about 17 ohms. And if the impedance is over here, it's 3 times 50, 150 ohms. No reactance. But what if I've got some resistance and reactance? I'm anywhere along the rim here. Let me stop. Does that make sense? I had to really think about that. If the SWR is 3 to 1, there are a gazillion different impedances that can result in an SWR of 3 to 1. Do I care at my radio which it is? Maybe not, but I can measure it. See, I don't know how to interpret silence. If this were a live class, I'd see your faces and I could tell, oh, what I said, that's totally confusing. So what I'm suggesting here is on a Smith chart, you can't tell the impedance by knowing the SWR. You just know it's somewhere on the rim of that circle. Did that statement make sense in English?
Yeah.
Okay. So see where I'm going? I'm getting worse and worse. Now my SWR is 4 to 1, reflection 60%. Now I'm way out here. I'm getting what? Farther from the bullseye. I don't like that. My radio doesn't like it. SWR is 20 to 1. Well, no radio is going to work like that. I'm reflecting 90% of the energy I send to the antenna. That's not going to work. 100% reflected. So 100% reflected means what? SWR is infinitely high. It means, look, that's as bad as I can get. Someone said, what if I miss the chart? Throw it into the door. Well, you can't do that on this. This is as bad as it gets. You're on the rim. So, time for a quiz. So I'm going to force you guys to talk. Now, you can talk in Portuguese. So here's a fake antenna. Okay, it's not real. So here's a Smith chart of my antenna. And I take measurements A, B, C, D, E. My question is, where is the antenna resonant? I'm going to stop talking. You guys discuss it. You can talk in Portuguese.
D. Point
D, right?
No D não tem reatância nenhuma, é puramente resistivo.
Now maybe there's more than one answer, or maybe it's not resonant anywhere. I'm being vague about this.
Near the bullseye, in the center.
Okay, so let's review again. Near the bullseye. What does resonant mean? It means the reactance is 0.
Yeah.
Where on this chart is the reactant 0? A?
B and D.
No.
B and D.
B? Yes. B is no. B isn't close to the bullseye for sure, but B is no reactants. It's on the horizontal axis. How about C? No. D. Yeah. Oh yeah. D as well. So B and D, Baker and Dog. B and D are resonant points on this graph, meaning no reactants. Now, some of you, I think, were thinking of this question, which I did not ask. Where's the SWR lowest? A, B, C, D, E.
That would be C.
In C.
C.
Yes, C. Why?
But it's nearer to the bullseye.
You got it. So I remember I made the bullseye 50 ohms when I calibrated it. I didn't tell you that, but usually we do. All right, now I'm going to try to trick you, right? My students know this. I always try to trick them. Now, where's the SWR lowest? A, B, C, D. And I made the center 50 ohms.
It's all the same.
No matter.
All right, you guys are good. So A, B, C, and D, the SWR is equally bad or equally good. It looks like maybe 2 or 3 to 1. Yeah. How do I know they're equally bad? Because I don't care what the impedance is. They're all equally distant from the bullseye. So SWR think, how far from the bullseye? Impedance think, well, what's the R and the X values? So we good?
Yeah.
Where is the resistance the least? A, B, C, D.
Resistance, B or C is the lowest resistance.
Remember, where's resistance on the horizontal axis?
It's near the x-axis.
Yeah.
It's all resistance is the x-axis. Down here is this lower high resistance. Remember that?
Lower.
Yeah.
So that's 0.
I mean
and over here,
A
resistance
or
is.
D.
Changed your mind. So the resistance is least. Well, what? Where you're closest to over here? A and D, least resistance. Where's the resistance the greatest?
The greatest, I would say.
Bravo.
B or C, like
B
I
or
said.
C. B or C. Where's the reactance the least? See, now I'm going to trick
A.
you.
It's
A?
A. It's
A.
positive and it's A.
Where's the reactance the least?
The least it's A.
A
A.
Or
D.
D?
Yes.
Well, pretty close. Where's the reactance the greatest?
B or C.
B or C. I didn't draw it as well as I should have, but okay. So you guys are getting pretty good here, and you're getting used to me here, okay? So this is a hard question. So I put up an antenna, and I know a little about impedance. You know, I've used that word. My ninth graders would always call it impedance because they wanted to, you know, get under my skin. So impedance. That's an R value and an X value. At resonance, the X value should be 0. And R, well, for a dipole in a tree, maybe 50, 60, 70 ohms, something like that. But if I move off the resonant frequency, now this is a hard question. Which is changing faster, the resistance or the reactance, when I move off the resonant frequency?
X.
I heard X, reactance.
Yes,
That's
I said X.
Lucian. Any other ideas? Which changes faster, the X or the R, if we move off the resonant frequency? Hard question, isn't it? Probably no one's ever asked you that before.
No.
Well, if you are going off the resonance, you are going off the bullseye, right?
Yes.
So I would say R.
So let's talk about resistance. What is resistance in an antenna? A wire antenna, not a beam or something fancy. What's resistance? Well, resistance means the feed line comes up and sees the antenna as a number. That's the resistance of the wire compared to some other conductor. So the resistance of half-wave dipoles in space, not near anything else, is about 70 ohms. Debated, but around 70 ohms. So not a bad match to 50 ohm coax. If you go off the resonance, that's going to change a little bit. Usually as you make wires longer, usually the resistance goes up. Usually when you make wires shorter, the resistance goes down. That's just the way. Now we're talking about something referred to as radiation resistance. Okay, what's the X? The X is harder to describe. The X is the reactance. What does that mean? It means now my antenna is behaving more like a capacitor or an inductor. Is that going to dominate the impedance, or is the resistance going to dominate? So here's an example I found of a real antenna. So the graph is a little different, not a Smith chart. So here's reactance and 0. It came out a little blurry. 0 reactance means resonance. So this antenna is resonant right here. 3.65, I don't know if you can read this, 3.65 megahertz. Resonant frequency. So it's a dipole. Now, why isn't it 50 or 60 ohms? Oh, because this is a real dipole near real what? Earth. So when you take an 80-meter dipole and put it up, let's say, 20 feet above the ground or 30 feet or 40 feet above the ground, there's another conductor nearby. What's that other conductor? The Earth, ground. The Earth's not a very good conductor. Well, radio frequencies is pretty good. So wait a minute, what's happening? So you're going to get a reflection off the ground that comes right back into the antenna. So the feed line is going to see the effect of the original wave and a reflected wave. Oh, well, that changed the impedance of the antenna, the ground. Yes, that has a dominant effect on antennas. And all hams know when you raise the dipole, it lowers the angle of radiation, all that kind of stuff. It changes the impedance. So low dipoles on 80 meters will often have an impedance of like 10, 20, 30 ohms, nowhere close to 50 ohms. To get 50 ohms, you have to put it up like 100 feet in the air. And not many of us can do that. So look what happens here. The resistance is about 40 ohms, probably because it's close to the ground. As I move off frequency, 3.8 megahertz, the resistance part is about 55 ohms. So the resistance went from 40 to 55, from 3.65 to 3.8. So the resistance did change, right? Went up a little bit. How about the reactance? Well, up here, oh, look, the reactance is 50 ohms. How about down here? Oh, the reactance is negative 50, 60 ohms. So in the case of a dipole, the reactance is changing much faster than the resistance. That's interesting. And your little NanoVNA can show you. This was not a graph that came out of the NanoVNA. So let's take a look at something. Here's my 80-meter antenna. This is my 80-meter antenna. And I'm measuring it from my shack at the end of 150 feet of coax. So position 1, 3.5 megahertz right here. I'm not close to the bullseye. Position 2, 3.6 megahertz. I'm right in the bullseye. Position 3, 4, 5, 3, 4, 5, 6. So I'm going to ask you, where is my antenna resonant? I'm just looking at the Smith chart now.
2 and 3.
Unmute, call it out.
2.
Where is my antenna resonant?
2
I hear 2
And
and
3.
3.
and 3. 2 points. Yes, that's true. 2 and 3. What? Yes. Well, 2, however, is close to the bullseye, right? So 2, I imagine, is going to be a good low SWR, maybe close to 1 to 1. 3, well, wait a minute. 3 is far from the bullseye. I know that's not good. But wait a minute. 3 is also resonant. Yeah, but that doesn't help me. The SWR at position 3 might be 3 to 1. It's resonant. No, wait, be careful. It's resonant because my coax is part of the antenna. Does the coax change the resonant frequency of my antenna system? Yes. yes. Where is the SWR lowest? Oh, close to the bullseye. 2. All right, so wait a minute now. So I set up my antenna, and it works really well at 3600 kilohertz because that's where I love to operate. Now I got to get on the phone part of the band. What am I going to do? I know what I'm going to do. I'm going to climb up my antenna and cut off 10 feet. No, I'm not going to do that. I need to fix this problem. Where? I don't want to fix it at my antenna. I'm going to fix it in my shack. I say, radio, come on, get with it. So on my radio, it has this little button. It's called antenna tuner. And I press it and it goes bzz, bzz, bzz. And now the SWR is 1 to 1. Well, how did that happen? It's like, that was magic. So let's take a look at what we can do to move the antenna impedance. We want to move it from some bad value up here. Let's say this is my antenna impedance. I want to move it from here to the bullseye. How do I do that? I need a antenna tuner. What does that mean? I need to what? Cancel the reactance. Does this point have reactance? Yes. How much? Hey, 25 ohms. How do I know that? Because my NanoVNA is showing me that. See, my little silly SWR meter doesn't give me that information. My NanoVNA does. Now, it's also got 10 ohm resistance. That's not good either. So I've got two problems here. My resistance is too low, and my reactance is not zero. Both conditions are bad. I want to be in the bullseye. Okay, I'm greedy. I want to be right in the bullseye. Come on. What do? I build an antenna tuner. Oh, yeah? What does that mean? It means all I need to do is what? Cancel that 25 ohms of, in this case, it's inductive reactance. Cancel that in my shack. How do I do that? Oh, I know. I do it with a capacitor, right? I provide in my antenna tuner 25 ohms of the other kind of reactance. I mean, I said the bad kind. There's no such thing as the good and the bad reactance. They're all bad. So what do? I have to design a circuit. How do I know how to do that? All right, so we're almost near the end of my talk. Inductors and capacitors move the impedance points on a Smith chart. I had to really think about that. If I add a series inductor, it moves this way. A parallel conductor moves this way. A series capacitor moves this way. And a parallel. So basically, if I hook up capacitors and inductors, either in series or parallel, I can move my antenna impedance to 50 ohms. How do I know what to do? Well, I got to try this and see what works. So basically, there's a chart like this that says forbidden region. I don't want to be here. But if my antenna is anywhere in here, this circuit will work. ZL, that's the load. That's my antenna. Z sub S, the source. That's my radio. So if my impedance is anywhere in here, and between my radio and my feed line, I hook up this kind of a circuit, I can move with the proper values. I can move the impedance to the bullseye. Oh, I like that. Over here, notice the ZL now has a series coil and a capacitor in parallel. See, it's reversed here. So anything in here, I can move this low value to the 50 ohm bullseye. Oh, that's cool. How about the other possibilities? What if I'm up here? Then I need this kind of a circuit, a parallel capacitor and a series inductor. I'll move any impedance here to the bullseye. Or if I'm here, these are low values, right? And these are mostly up here, inductive. So my capacitor is what? Kind of canceling the inductive reactance, and the inductor is moving it to... So I need at least two components. Now I can have 3 or 4 or 12 components, but at least two, because I need to cancel the reactance and move the resistance to the bullseye. So here's a simple 2-component circuit that almost everyone who works with long wires knows. If I just have a long wire, 100 feet of wire in a tree, and I hook it up, I always put a parallel capacitor and a series inductor. If I make this a variable and this variable, I can eventually, by adjusting these two, move any random wire to 50 ohms resistance. Magic. What does this cost? $20 maybe parts. A chassis, a couple parts, a knob. How about this one? Oh, what if my antenna is a low impedance and I want to bring it up to 50 ohms? Then I have a series coil and a parallel capacitor, and if I choose these the right values, I can move any low value of impedance to 50 ohms. So in general, a simple antenna tuner does this. It can have any one of these 4 designs, or by a switch, move them around. The capacitor is in series, the inductor is going to ground. Now, the capacitor is on the one side, here the capacitor is on the other side. Does that make a difference? Yes, because here's the antenna. The first thing it sees is the parallel capacitor, inductor to ground. Whereas here, the first thing it sees is a series capacitor. And the same thing here. So there's 4 possibilities. But if I have an inductor and a capacitor, I can hook them up with switches, and I'll eventually be able to tune any impedance and convert it to 50 ohms, or almost any impedance. So here's what they look like. Instead of being an L, they get away with 2 L circuits, meaning a T network. So what do you need for this? You need 2 capacitors, and here's a little simple MFJ tuner. Capacitor 1, capacitor 2. Here's the catch. Neither of these is grounded. Neither side is grounded. What is grounded? The coil. So the coil mounted this way, you can't see in here. The bottom of the coil is grounded to the shield. That means this thing has a shaft that you don't want to touch the chassis. Or if you touch it, you're going to get a shock. So here's a simple T-network tuner. Here's another one. It was built into all the old tube radios. The vacuum tubes have a pretty high voltage and a low current, so impedance of like 1 to 5,000 ohms. That's really high. You want to match that impedance to an antenna, 50 ohm coax. Whoa, that's huge. So inside the radio itself, it had what was called a pi network tuner. Capacitor called a tuning capacitor. A coil, often this had taps, and another capacitor called the output or loading capacitor. So this had 3 adjustments. And if you can get the 3 just right, you can get your radio, let's say 80 meters, tuned to your dipole. Here's what it looked like. And this wasn't one of my radios, but I had a lot of radios that looked like this. 2 capacitors and a coil. Here's the coil, and this big heavy thing was like your coil for 10 meters. And this was a coil for the rest of it. I'm going to jump ahead. So here's a Smith chart. That's a slide rule. A friend of mine has this. And I said, oh, man, you know, he's in his 90s. I said, did you ever use this? He's an engineer, retired. He retired 40 years ago. He said, yeah, when I was doing stuff. Well, I gave you a little bit. What I did was play with different circuits to see if I could measure with my NanoVNA what a physical circuit looks like, an RLC circuit. And I've played with it, and I tried, and I learned about the through signal. I could talk about that if you want me to, but let me stop and ask if there are any questions up to this point. That was quite a bit under the hood.
Barry, you have explained it well. How can we compensate inductive reactance with the opposite, and to get only the resistive part of the antenna? I understand that, but if as we watch in your in a slide, we have 2 points of resonance with 2 different values of the resistance part.
Yes.
So we can, with the antenna tuner, we can change the reactance, but we cannot change the radiation resistance of the antenna.
Not at the antenna. That's correct. Whatever I'm doing in my shack with my magic antenna tuner, am I changing what happens where the feed line meets the antenna? No. But the bad stuff here, the reactance, is canceled in my shack by another bad thing, reactance. So my radio sees no reactance. My transmitter is happy. But yes, that's an important fact. Does my antenna tuner tune my antenna? Well, not if my antenna is just the wire in the tree. No, it doesn't tune that.
Okay.
That's a good point. No.
Barry,
but it's making my transmitter develop full power. My transmitter, what does my transmitter see? 50 ohm load. My transmitter's in the bullseye. I don't care what's happening out in the trees as long as I'm making contacts all over the world.
Okay. And the other question I have is there a, if I use a balloon transformer, perhaps, I don't know, some kind of balloon in the feed point, the antenna feed point, can this can turn the feed line less, the antenna less dependent on the influence of the feed line or the length of the feed line?
Neither. No. No and no. All right, here it is. There we go. All right, so let's look at this. That is a good question. And I thought about it over the last month, and I added this slide, but after I talked to you guys. So let's look at this. This wire antenna, there's 2 sides, and here's an insulator. So this side is, let's say, a quarter wavelength. This is a quarter wavelength. Overall, my antenna is 1/2 wavelength. Okay so far?
Okay.
Yeah.
My feed line has two wires, a center and a shield, the braid. The center goes over here, so the center conductor connects to 1/4 wavelength. The shield, the braid, connects to 1/4 wavelength. Now here's a question, so I really want to stop and ask you to think about this. Which half of the antenna radiates the most? The side connected to the center conductor or the side connected to the shield or braid? Which side of the antenna radiates the most?
It's the same amount.
I would say the same. That's a tricky question.
A shield.
So you know me by now. That is a trick question. So it's the same. I didn't say that as a all trick. They're the same. Why are they the same? Because they get the same amount of current.
Exactly.
So on the feed line, even though it's coax, is the same current going through this wire and the shield, but in opposite directions. Is the current the same value? Yes.
Yes.
Yeah, supposedly, yes. But now be careful. The center conductor, the current only has one choice, to go out here and then back. Here's like Grampy, out here and back. The shield, now the shield's on the outside of the coax. At radio frequencies, the current can stay right along the edge of a conductor, called the skin effect in English. I don't know if that has a Portuguese equivalent, the skin effect. So what if current comes up the shield from the transmitter, comes up the shield, the braid, and comes here, and some of the current goes out on this part of the antenna, but the other part of the current goes back down the shield on the outside of the shield. In other words, the shield really is two wires, the inside of the shield and the outside of the shield. Oh, wait a minute, it's one wire. No, not at RF. At RF frequencies, the shield can have a current going on the inside of the wire and the outside of the wire separately.
It's like a
So wait a
membrane.
minute. That means what? Part of my antenna current is coming back down the coax. Oh, is that a problem? Yes, that's a problem. Why is that a problem? Because then my coax is radiating. I don't care about that. Oh, well, you don't care about that? Then when the coax comes in your shack, you're going to get RF all in your shack. Oh, now you touch a microphone and you get a little shock here and there. That's bad. So how do I prevent the current in the braid here? How do I prevent that? Where's my mouse here? How do I prevent that current from going right back down the outside of the coax? I put on one of these called a balun, B-A-L-U-N, balanced to unbalanced. Balanced? What's balanced? The antenna. What's unbalanced? The coax. So what is this? This prevents the current from coming back down the outside of the shield. Now there are two types of baluns. Something called a voltage balun and something called a current balun. And they operate on different principles. But they both try to prevent the feed line from becoming part of the antenna. If you have current coming back down the outside of the shield, you can determine that a simple way. Let's say you have an SWR meter in your shack and you're transmitting with, let's say, 50 watts. And you read the meter and it has an SWR value. With your hand, grab the coax. Now it's still plugged in, right? Everything's grab the coax and move your hand along the coax. See if the SWR meter goes up and down. It shouldn't, right? But your hand is now a capacitor to your coax, and you're going to get some radiation, and not so good. If you do that and get a shock, then you know you're real bad. So the question is, does this balun affect the impedance up at the antenna? No. Well, it's hard to say. What it does do is force the current to stay on the antenna rather than come down the coax itself. Can my dipole work without this? Maybe. Probably. But can I get into trouble and get RF in my shack if I don't have one of these? Definitely. That's happened to me. So when I put up a dipole, I always put on these things. They're called baluns. They may have different shapes, but that's kind of where we are. Let me see if I can jump down to something else that I thought. I don't have time for this. Is this still live here?
Yep.
Yeah.
All right, so let me show you one. Oh, from current slide. Okay, so here's something else that I've been playing with this week. So I wanted to look not so much at antennas. After a while, antennas got boring. And I understood them, I fixed them, so what else can I play with on this gadget? I want to play with my stethoscope on little circuits. So remember, it has two. It has an in and an out, a channel 0 and a channel 1. The signal that comes back on channel 1 we call S11. Out port 1, back port 1. S21 is different. The signal that comes into port 2 from port 1. So the S2 is down here. So I send out a signal, it goes through something, no, not an antenna. And what comes out goes into port 2, and port 2 automatically has a 50 ohm load. So I thought, look what I found. I did this just yesterday. And so I was working on this yesterday. Look what I found in my junk box. I have no idea why I got this or what it is, but it looks to me like a little antenna trap, right? I can see it's a trap because this side and this side are two different diameters, and there's obviously a coil. There's a screwdriver, so I can short out some taps. I thought, I wonder why I bought this. I don't remember. What resonant frequency can I use this on as an antenna trap? I thought, oh, good. I'll hook up my $50 NanoVNA. So how do I do that? I make this the through signal. So I hook it up and I say to my NanoVNA saver, show me the S21. That's the through or the gain. And show me also the S21 phase, because I think I understand phase. So look, I ping from 15 megahertz to 35 megahertz, because I know it's not an 80 meter trap, but I don't know if it's a 2 meter or 6 meter trap. So I tried this, and look what happens. The gain. Gain means what goes through the device. Through the device. 0. 0 is no loss. Negative 30, that's a big loss. So I lose a lot right here. Marker 3, that's 25 megahertz. Oh, I know why I bought this. It's a 12 meter trap. 12 meters is about 24.9 megahertz. I don't operate there, but I could with this little trap. But look, more signal goes through at a higher frequency and at a lower frequency. How does that happen? Oh, the lower frequencies go through the coil. The higher frequencies go through the capacitor, not the coil. Coils block high frequencies. Capacitors block low frequencies. So I said, if I'm thinking correctly, then let's look at the phase. Phase, what does that mean? I'm looking at the voltage and the current that goes through the device. Negative, positive up here. Here's about 0 in here. So I'm off a little bit, but it looks like the phase goes from negative to positive somewhere around 26 megahertz. Now, I connected this with sloppy wires and things, so I didn't do it very well. I thought, oh, cool. So I used my little NanoVNA that I didn't buy, right? And I figured out something about this junk part. If I want to adjust it a little bit, I've got to undo the screw here and move the coil back and forth because I can't change the capacitor. Now, this is what just fell on the floor. I've been playing with this all day. I had so much fun. I mean, I understand how resistors, inductors, capacitors work, but I said, I want to see if I'm right about this. So 50 ohm resistor, 200 picofarad capacitor, about a 10 microhenry air inductor. So if I set this for most of the coils, this for halfway, 50 ohms, what's the resonant frequency here? Oh, can my NanoVNA tell me? Sure, I know how to do that now. So what do? I've hooked them up in series. Why in series? Because in series, I'll get the most current at resonance. Remember that? In series. So in series, the current has to get through the capacitor and the coil. Low frequencies can't get through the capacitor. They get blocked. High frequencies can't get through the coil. They get blocked. But the resonant frequency gets sort of through both. Least, not 0, but least resistance impedance, meaning the most current. Let's see if that's what happens. So I hook it up. Here we go. So I went overboard. So here's all 6 graphs with my NanoVNA saver. So here's a Smith chart. Oh, cool. I get this. Look. 1, 2, 3. And now it's not near the bullseye. And I had to think why. Oh, I know why. Dummy. You know what I did wrong? Look. My NanoVNA S21 here. This port already has a 50 ohm terminated resistance. It's already built in. So when I built this, I put in a 50 ohm load, and I thought, oh yeah, I need a 50 ohm load. No, the load's already in the gadget. So I made it, 100 ohms. I didn't know that until I got the graph. So look at this. The SWR, well, it's lowest here. We're at about 3600 kilohertz. Oh, so my tuned circuit here, capacitor about halfway, a lot of the inductance. This circuit, I don't care about that. This circuit is tuned for 80 meters. Well, I kind of knew that. Okay, so what about this graph? Oh, look at this. Now, wait a minute. There's red and there's blue. The blue is the S11, what comes back out of the device. The red is what goes through the device. Now, let me think. Series. That should be maximum at resonance. What gets through? Yeah, look. Here's the maximum. I'm looking at the, what's this? S11 is in blue, S21. The red is what goes through. What gets through is the most at the resonant frequency. The blue is the reflected. What comes back at the resonant frequency? Nothing's coming back. It's like, oh, it's got the biggest loss. Remember? It always confused me. Let's look at the resistance and reactance. Ah, that was my question. So on this little circuit I built, this is not an antenna. It's a little LC circuit. The resistance is blue. What's the resistance? Oh, about 200 ohms. Oh, yeah, because I put in 50, and there's 50 already there, and I'm guessing here. But what about the reactance? It's way up here. 600 ohms at the resonant frequency. Oh, cool. How about the SWR? Yeah, that makes sense. It's minimum at 80 meters. I've made an 80-meter series tuned circuit. All right. Now, we're up to 12th grade. You ready? What if I look at the phase on the reflected and the phase on the through? Ah, I'm looking at the timing of the voltage and current that comes back and the voltage and current that gets through. What happens at resonance? The phase should be, what magic number?
0.
Guess what? I just learned that about an hour before I talked to you guys. I thought I knew it would happen. But when I made this graph, I thought, that's so cool. I quickly did a screenshot, saved it. But I'm looking at the clock, and I'm keeping you guys up, and it's, I have other slides. I need to stop. I could go on really for another hour. This is so much fun. But the NanoVNA, I found every day when I play with it, it's like a new instrument. It's a new toy. I learn something new every day.